Welcome to another episode. Before we begin, take a moment to leave a comment telling us where you're listening from and what time it is there. It's always fascinating to see this web of moments we share across the world. Different clocks, different skies, all ticking toward the same curiosity. And if you enjoy drifting through these explorations with me, I invite you to subscribe so we can keep traveling together through the quiet corners of knowledge. Now, imagine two twins. They're identical in every way. Born on the same day, with the same laugh, the same restless imagination. But one of them, let's call her Anna, dreams not of the world she sees, but of the stars beyond it. Her brother, Leo, stays home, content under Earth's familiar sky. One day, Anna steps aboard a spacecraft capable of extraordinary speed, something close to the speed of light itself. She promises Leo she'll return. The engines ignite, the stars stretch into lines, and the ship becomes a streak of light fading into the black. Years pass on Earth. Leo grows older, watches cities change, seasons shift, maybe even grows grey around the temples. Then, one day, the sky flares again. Anna's ship descends, silent and shimmering, and the hatch opens. Out steps his sister, young, barely older than when she left. To her, the journey felt like a few years. To him, decades. And yet neither did anything wrong. No tricks, no illusions, just physics. That's the twin paradox, a simple story that manages to bend our intuition until it nearly breaks. It sounds like science fiction, but it's not. It's a direct consequence of a universe where space and time are not what we once thought they were. It's one of the most famous thought experiments in all of physics. An idea that Einstein never officially published as a story, but which arose naturally from the strange logic of his theory of relativity. The twin paradox is one of those rare things that takes an everyday word, time, and quietly destroys its simplicity. It makes us realize that time, that invisible thread we live inside, doesn't tick the same for everyone. It depends on motion, on gravity, on perspective. To understand it, we don't need equations, at least not tonight. What we need is imagination, because relativity began, not in equations, but in thought. Einstein himself used to say that he was a man who visualized. Long before he became the icon of genius with the unkempt hair, he was a young patent clerk in Bern, watching trains arrive at the station, wondering how time would look from different frames of reference. He imagined riding on a beam of light, an impossible thing to do, and asked himself what the world would look like if you could. Would a mirror still reflect your face if you were moving alongside the light that left it? Would lightning strike both ends of a train at the same moment if you were standing on the platform, or if you were aboard the train itself? These were not riddles about trains and lightning. They were questions about the fabric of reality. From those musings came special relativity in 1905, a theory that told humanity, in no uncertain terms, that time and space are not absolute. They're woven together, forming a single fabric called Spacetime. And when you move through space, you necessarily move differently through the other, through time. In other words, the faster you travel through space, the slower you travel through time. That's not poetry. It's measurable. It's been tested, proven, and built into the technology you might be using right now to listen to this. GPS satellites orbiting Earth have to correct their clocks for relativity, both for their speed and for the weaker gravity they experience above the surface. If they didn't, the system would drift by kilometers each day. Time really does run differently at different altitudes and velocities. But Einstein's discovery was not initially intuitive. Before 1905, people thought of time as universal. It flowed like a great river, the same for everyone, everywhere. If two clocks ticked in sync, they would stay in sync, no matter how far apart you carried them. That was the Newtonian view. Space was the stage, time was the metronome, and physics played upon it. Einstein shattered that stage. In his world, the speed of light, about 300,000 kilometers per second, or roughly 186,000 miles per second, was the one constant that no one could outrun or slow down. Whether you're standing still or flying past at enormous speed, light always moves away from you at exactly that pace. And if light's speed never changes, then something else has to give. That something is time itself. When motion increases, time must slow down to keep the universe's rules consistent. That's what happens to Anna in our story. From her perspective, she simply travels away, turns around, and returns. Her clock ticks normally, for her. But from Leo's point of view, her clock runs slow, her heartbeat slows, her journey stretches out. And yet, strangely, when she returns, it's his clock that shows more time has passed. How can both be right? That's the crux of the paradox. When this story first began to circulate in the early 20th century, it genuinely troubled people. Not because the math was wrong, the math was impeccable, but because human intuition wasn't built for relativistic speeds. Our everyday experience of time is rooted in the slow-motion world of walking and breathing and sunrise to sunset, where relativity's effects are vanishingly small. If you walked at a brisk 5 kilometers per hour, about 3 miles per hour, the time dilation would be on the order of 1 part in 10 to the 16th. That's less than a trillionth of a second per day. Nothing you'd ever notice. But as you approach the speed of light, those fractions grow enormous. At 90% of light speed, time for the traveller slows by more than half compared to someone standing still. At 99.9%, a year for the traveller could mean decades on Earth. Einstein had effectively written a new kind of clock, one that depended on motion. To truly understand why this happens, physicists often imagine a light clock. It's a simple mental device, a beam of light bouncing between two mirrors. Every bounce is a tick of the clock. If the clock is stationary, the light travels straight up and down. But if the clock is moving sideways, that light has to travel a diagonal path, a longer one, to hit the mirror. And since the speed of light is constant, that longer path means it takes more time between ticks. The faster the clock moves, the longer each tick becomes, and time itself slows. You can visualize it. Each of us carries such a clock inside us, our atoms, our cells, our thoughts. When you move fast enough, even your very sense of now begins to bend. It's a hauntingly beautiful idea. Motion and time entangled, inseparable. When the twin paradox is first explained, many people instinctively protest. But couldn't the situation be reversed? Couldn't Leo say she was the one moving and he the one standing still? That's the natural question, because relativity says all uniform motion is relative. But the trick lies in something subtle: acceleration. During her journey, Anna turns around. She changes direction. That moment of acceleration breaks the symmetry. She experiences a different path through space-time, and that makes all the difference. We'll explore that in more depth later, but for now, it's enough to know that time is not absolute. It's tied to how we move. It's tied to gravity. It's tied to the geometry of the universe itself. When you realize that, the twin paradox stops being a puzzle and starts feeling like poetry. Two lives diverging not through choice or fate, but through the way space-time curves around their journeys. And perhaps beneath the physics there's something quietly human in it too. All of us experience time differently, even at our everyday pace. A year in youth feels like a lifetime. A year in adulthood feels like a blink. The paradox just makes literal what we already feel. That time is personal. It flows at the rhythm of our motion, our perspective, our story. When Einstein introduced relativity to the world, he once wrote that the distinction between past, present and future is only a stubbornly persistent illusion. It wasn't meant as mysticism. It was a statement of geometry. To him, all moments already existed within space-time. We simply move through them, tracing our own world lines, like threads woven through a vast cosmic tapestry. The twin paradox, then, is not really about twins. It's about the universe telling us something fundamental, that now is not universal, that there are as many clocks as there are observers, and that every journey, every life, writes its own unique rhythm of time. So tonight, as you listen, you can imagine Anna's ship coasting silently among the stars, her heartbeat slower, her Her dreams stretched like light itself across the vacuum. And on Earth, her brother looking up at the same constellations, growing older under their cold, steady light. 2 lives, 2 clocks, 1 universe, all perfectly consistent. Only our intuition finds it strange. That's the paradox. Einstein once said that imagination is more important than knowledge, and nowhere does that feel truer than in the story of how he redefined time itself. Because before the twin paradox could even exist, humanity had to discover that time could bend. And that discovery began, strangely enough, not with clocks, but with light. In the late 19th century, physics seemed almost complete. Newton's laws explained motion, Maxwell's equations described electromagnetism, and chemistry had settled into a confident order. If you were a scientist around 1880, you might have believed the universe was a perfectly wound clockwork, precise, elegant, and entirely understood. The only missing piece, so people thought, was the mysterious medium through which light travelled. They called it the luminiferous ether. In a world where every wave needed something to ripple through, water for ocean waves, air for sound, it seemed obvious that light too must have a medium. The ether, they imagined, filled all of space, invisible but real, a kind of cosmic jelly that carried light's vibrations at tremendous speed. If light was a wave, it had to wave through something. The logic was simple enough, and for decades, nearly every physicist believed it. But then came an experiment that quietly cracked the universe open. In 1887, 2 American scientists, Albert Michelson and Edward Morley, built one of the most precise instruments ever constructed, an interferometer. Its purpose was beautifully simple. As Earth moved through space, it should be moving through the ether just as a swimmer moves through water. So, light beams travelling along the direction of Earth's motion should be slowed slightly compared to beams travelling sideways to it. By comparing the two, Michelson and Morley expected to detect the ether wind, the gentle drag of space itself. They found nothing. No matter how they turned their apparatus, the light waves arrived in perfect synchrony. The speed of light remained the same in all directions. It was one of the most important null results in history. They had searched for something that wasn't there. For a while, physicists tried to patch the theory. Maybe the ether clung to Earth, they suggested. Maybe objects moving through it contracted slightly, compensating for the effect. The mathematician Hendrik Lorentz even formalized that contraction, a brilliant guess that would later become a cornerstone of relativity. But the underlying assumption remained. Surely something must be out there carrying the light. And then came Einstein. In 1905, working as a 26-year-old clerk at the Swiss Patent Office, Einstein published a series of papers that would later be called the Annus Mirabilis, the miracle year. Within months, he proposed an explanation for the photoelectric effect, for which he'd eventually win the Nobel Prize, offered a new model for Brownian motion, introduced the equivalence of mass and energy, E equals mc squared, and tucked quietly among them a paper titled On the Electrodynamics of Moving Bodies. It was the paper that rewrote time. In that short and surprisingly readable work, Einstein did something radical. He took the results of Michelson and Morley seriously. Instead of trying to fix the ether theory, he threw the ether away altogether. He said, in essence, maybe there is no universal rest frame. Maybe light doesn't need a medium. Maybe the speed of light is simply the same for everyone, in every direction, no matter how fast they're moving. It sounds innocent, but the consequences are staggering, because if the speed of light is constant, then time and space cannot be. Imagine 2 people, one standing still, the other moving rapidly. Both shine a flashlight. If light's speed is the same for both, then their measures of distance and duration must adjust to make it so. One's rulers shrink, the other's clocks slow, and what one calls simultaneous, the other may call sequential. The universe bends its bookkeeping to protect the speed of light. That single idea dismantled centuries of assumption. Newton's time, absolute, universal, flowing equally for all, was gone. Space and time became flexible, interwoven, dependent on motion. When Einstein later explained it, he often used the image of lightning striking both ends of a moving train. Suppose you stand on a station platform and see two bolts hit the front and rear of a train at precisely the same moment. To you, they are simultaneous, but to a passenger riding the train, things look different. Because the train is moving forward, the light from the strike at the front has to chase them, while the light from the strike at the rear is racing toward them. The passenger therefore sees the rear flash first and the front flash later. Both observers are correct. Their disagreement isn't about perception, but about what simultaneous means. That is the revolution of relativity. Simultaneity itself is relative. There is no universal now. Every observer slices the universe into past and future in their own way, depending on how they move. What is now for you may already be then for someone speeding past. If that feels unsettling, it should. For thousands of years, humans assumed time was a shared stage, the same everywhere, ticking beneath our feet like a hidden drum. Einstein revealed that it's more like a thread woven through each traveller's path, personal, unique, yet consistent within the grand geometry of space-time. It's worth pausing here to appreciate how daring this was. Einstein didn't have experimental proof in 1905. He had logic, mathematics, and an almost philosophical conviction that the laws of physics should look the same to all observers moving at constant speed. From that simple demand, he derived the entire structure of special relativity. And astonishingly, it worked. Within years, predictions born from his equations were confirmed. Clocks moving quickly really did tick slower. Mass increased with velocity. Even energy and matter, long treated as separate entities, turned out to be two faces of the same phenomenon. The elegant E equals mc squared followed naturally from his reasoning. Mass is simply frozen energy. Energy is moving mass. All of it stemmed from that one stubborn constant, the speed of light. So what does it really mean to say the speed of light is constant? It doesn't mean that light always travels at the same speed through every material. Glass slows it down, air bends it, but that in empty space, the universe's ultimate limit is the same for everyone, regardless of how they move. You could chase a photon at 99.99% of light speed, and still it would slip away from you at that same 300,000 kilometers per second, about 186,000 miles per second. No matter what you do, light refuses to be caught. That constancy anchors reality. It ties together cause and effect. It defines the ultimate speed limit for information, for influence, for anything that hopes to be real. When you look up at the stars tonight, you're seeing this principle in action. The light from Sirius has travelled about 8.5 years to reach your eyes. From the Andromeda Galaxy, it's about 2.5 million years old. You're literally looking into the past, not metaphorically, because light speed is finite, and the universe will not let it go faster. The past, in a very real sense, is what you see every time you look out into space. The constancy of light speed forces a kind of cosmic humility. It says, there is no single observer privileged above all others. There is no universal center, no fixed frame. Every observer's measurement of space and time is equally valid, even if they disagree. The universe accommodates all of them simultaneously by shaping itself around motion. That's what makes relativity beautiful. It's not chaos, it's harmony. Each traveller moves through the fabric of space-time in such a way that the laws of physics never contradict themselves. If one twin's time slows, it's not an error, it's geometry being consistent. And this geometry would soon gain a new language. In 1908, Hermann Minkowski, Einstein's former mathematics professor, took his students' equations and gave them form. Henceforth, space by itself and time by itself, he said, are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. He had defined space-time, a single four-dimensional stage where every event in the universe has coordinates of both space and time. The twin paradox, the bending of time, the relativity of simultaneity, all of it lives within this grand geometry. But before we get there, it's worth remembering how unlikely this revolution was. Einstein wasn't a famous professor or a laboratory head. He was a clerk reading patent applications for electromagnetic devices, thinking about how clocks synchronized across distant towns. His great insight may have been born not from telescopes or experiments, but from bureaucracy, from wondering how you could truly know that two clocks separated by kilometers were striking the same second. That question, how to define simultaneous, turned into the key that unlocked spacetime. He realized that simultaneity can only be established by exchanging signals, and signals travel at the speed of light. If light's travel time is the same in all directions, then defining now between distant places already assumes relativity. There is no global clock, only local ones, whispering to each other through the finite language of light. That's how the grand story of relativity began. Not in thunder or prophecy, but in quiet reasoning about synchronization. It's humbling, isn't it? The entire cosmos reinterpreted because someone refused to accept the convenience of an invisible ether, because a single experiment, patiently done, produced nothing, because a young man with no lab imagined what it would feel like to ride alongside a beam of light. From that, nothing came everything. The bending of space, the slowing of time, the merging of energy and matter, and the paradox of the twins that would captivate generations. So when we picture Anna's ship gliding between the stars, remember that her strange aging is not a fantasy. It is the logical, measurable outcome of the world Michelson, Morley, Lorentz, and Einstein revealed. Her slower heartbeat, her shorter now, all stem from that single, stubborn truth. Light's speed is constant, and the universe will twist time itself to make it so. And somewhere, perhaps Einstein would smile at that, because the twin paradox is not a paradox at all. It's a love letter written by physics to consistency. If you could hold time in your hand, you might imagine it as a smooth ribbon. You, Leo, Anna, all of us, sliding along it at the same steady pace. Relativity asks you to rotate that picture. Time is not a separate ribbon. It is woven with space. When you move more through space, you move a little less through time. And the rules that make that trade-off consistent are what physicists package, somewhat intimidatingly, under Lorentz transformations. Tonight, we unwrap the package without the algebra and look at the mechanism inside. Start with a device so simple it feels like a child's toy, a light clock. It's just two mirrors facing each other. A pulse of light bounces between them. Up, down, up, down. Each round trip is a tick. Nothing mysterious yet. But now imagine the clock at rest beside you. The light travels straight up and straight down. The path is short. The tick is quick. Slide that same clock past you at high speed. The light still bounces between the mirrors. But because the clock is moving sideways, the light must trace a diagonal path, up and forward, then down and forward. Diagonals are longer than straight lines, since light's speed in empty space is fixed about 300,000 kilometers per second, roughly 186,000 miles per second. A longer path means a longer time between ticks. That's the whole secret, right there. A moving clock ticks fewer times between shared events. Time has stretched for the traveller, not because the clock is broken, but because the geometry of space-time demands it. The Lorentz transformations are the careful bookkeeping that makes this precise. They say, if two observers are moving relative to each other at a constant speed, each will find that the other's moving clocks tick slow and the other's moving rulers shrink along the direction of motion. Slow and short aren't insults here. They're the universe's way of keeping the speed of light the same for everyone. The transformations also mix space and time in a coordinated way so that cause still precedes effect for every observer. That last part, causality, matters. Physics isn't willing to trade cause and effect for convenience. But that symmetry sounds like a stalemate, people say. If each sees the other's clock running slow, who actually ages less? The stalemate ends when the world lines, the actual paths through space-time, differ in shape. The twin who rockets away and returns experiences segments of very high speed and a turnaround. that path through the four-dimensional fabric is shorter in proper time, the time the traveller carries on their own wrist, than the stay-at-home twins' nearly straight, gentle path. You don't need to compute it, you can picture it. One life's path is a long, smooth thread. The other is a dart out and back with a sharp bend. The geometry, not any sleight of hand, decides who has fewer ticks. Fewer ticks means less aging. Light clocks help with intuition. Symmetry keeps us honest. Let's apply both to a slightly richer scene. Suppose Anna glides by Earth in her ship at an immense but sublight speed. From Leo's frame on Earth, Anna's light clock runs slow, and her measuring rods along the direction of motion look compressed. From Anna's frame, Earth is the thing moving. She could say Leo's clocks run slow and his rulers look compressed. Neither is wrong. The trick is that the pair do not remain in symmetrical motion for the whole story. Anna brakes, turns and accelerates for the rendezvous. That turn breaks the mirror symmetry between their experiences, even if the acceleration phase is brief compared to the long cruise. Their world lines diverge in shape, and the one with the sharper detour accumulates less proper time. If this all feels too neat, too much like the universe tidied its desk to please a mathematician, remember that we've measured it. In 1971, physicists placed atomic clocks aboard commercial jets and flew them around the world. Comparing the airborne clocks with a reference clock on the ground, they found the differences predicted by relativity. Tiny, yes, tens to hundreds of nanoseconds, but right where the theory said they would be. The east-going and west-going flights didn't match because the direction of motion relative to Earth's rotation changes the speed through space, and the average altitude changes the strength of gravity. Time dilation isn't science fiction. It's a line item on a lab report. You live with it every time your phone maps your walk. GPS satellites circle Earth at about 20,200 kilometers, around 12,550 miles above the surface, zipping along at roughly 14,000 kilometers per hour, about 8,700 miles per hour. Two relativistic effects play tug-of-war with their time. Because the satellites are moving fast, their onboard clocks tick slower than clocks on Earth. Special relativity's contribution. Because they're higher up in weaker gravity, their clocks tick faster than ours. General relativity's contribution. Add them, and you don't get zero. The gravitational speed-up wins. The net is on the order of a few dozen microseconds per day, about plus 38 microseconds if you want a number. If engineers didn't correct for that, GPS positions would drift by kilometers each day. Your map would be nonsense by lunchtime. We don't believe relativity because it is beautiful, though it is. We believe it because ignoring it breaks our machines. Let's return to the Lorentz rules conceptually and follow the chain that keeps everything consistent. First, all observers moving at constant speed agree on the laws of physics. That's the relativity principle. Second, the speed of light in vacuum is the same for all observers. Those two pillars together force a reshaping of our accounting system for space and time. To keep light's speed fixed, you can't allow everyone to carry the same idea of length and the same idea of duration from one frame to another. So the transformations say, when you translate a measurement from one moving frame to another, lengths along the direction of motion come out shorter. Time intervals between separated events can change, and most unsettling of all, simultaneity is not universal. Two events that one observer calls at the same time may be first this, then that for another. The light clock picture shows why. When you slide the clock, the diagonal path makes each tick take longer. If you try to rescue simultaneity, if you insist that two ticks far apart in space must line up as a single now for everyone, you will break either the constancy of light speed or the relativity principle. The cosmos refuses both. It chooses to bend now instead. This isn't sophistry. It is the price of a coherent universe with a finite cosmic speed limit. There is a subtlety worth savouring. Some people ask, why can't we just say the moving light clock's path is longer because space is distorted? Why mess with time? The reason is that space alone can't do all the work. Relativity spreads the burden. Lengths contract along motion and times dilate. Both matter and both happen exactly enough to keep light's speed the same and keep causes before effects. Think of it like an orchestra. If you only quiet the violins, the music goes wrong. You retune the whole ensemble, time, space, simultaneity, so the melody stays true. Now, the traveller's perspective. Inside the ship, Anna doesn't feel her own clock run slow. Her pulse is ordinary. Her tea steeps at the usual pace. That's important. Each of us is always at rest in our own frame. Time dilation is never a self-diagnosis. It shows up only in comparisons between frames when we bring clocks together again to read them side by side. That's why the reunion in the twin story matters. Without meeting again, we'd only have stories shouted across the void, each insisting the other's time is peculiar. The reunion gives a ledger with both entries in the same place. Physics does not gamble with promises. It gives you a way to settle accounts. If you want a feel for the scales, take something familiar. A passenger jet cruises around 900 kilometers per hour, about 560 miles per hour. At that speed, special relativistic time dilation is microscopic, fractions of a microsecond over many hours. Add altitude, and you add a gravitational tweak. Clocks higher up run a touch faster because gravity redshifts time less. The airplane experiments measured both. That's why the round-the-world flights came back with slightly different totals depending on direction. Speed and height combine differently when you fly with Earth's rotation or against it. In orbit, the numbers grow more interesting. Astronauts aboard the International Space Station travel at roughly 7.7 kilometers per second, about 17,200 miles per hour, at an altitude around 400 kilometers, 250 miles. Their high speed slows their clocks, their weaker gravity speeds them up. For the ISS, the speed effect dominates slightly, so astronauts age a smidge less than people on the ground. Not by days, by milliseconds over long stretches, but measurable. Space agencies track it. Timekeeping on board is not a philosophical afterthought, but a navigational requirement. All of that fits the same blueprint. Your proper time, the time your body and your watch experience, is the length of your path through space-time. Not length in meters, but length in this four-dimensional geometry. Straight world lines at gentle speeds collect more proper time between two meetings. Sharply bent, high-speed world lines collect less. That is why returning travellers can, without contradiction, be younger than those who waited. No paradox, just the universe paying out according to the route taken. To really see how the Lorentz rules keep peace between observers, imagine a pair of beacons far apart in space that flash simultaneously for Leo on Earth. In Anna's fast frame as she rushes past, those two flashes are not simultaneous. One leads the other by just enough to keep the speed of light the same and to make sure Anna and Leo never disagree about what can cause what. The algebra that enforces this is what you find in textbooks, but the heart of it is simple. When space and time mix, at the same time, becomes a local idea. You do not define distant now by decree. You define it by exchanging signals, and signals take time. That's where the relativity of simultaneity comes from. Not from clever wordplay, but from finite signal speed. There's a lovely human echo in that. We too define our now by signals, messages, calls, the light in someone's eyes. None of those are instantaneous. Even in daily life, our sense of a shared moment is stitched together by delays. Physics just makes that stitching exact. If you still feel the urge to rescue a universal time, you're in good company. Our brains evolved for running and cooking and building, where speeds are tiny compared to light and gravitational differences over a few floors of a building don't matter. In that slow world, Newton's time is an excellent approximation. But technology keeps nudging us into the fast, the precise, and the high. The closer we get to the edges, satellites, particle beams, deep space probes, the more the true rules show. Our machines now rely on them quietly, like a city relying on a distant reservoir it seldom sees. There's one more symmetry to appreciate. If Anna were to make the journey not as a sudden dash, but as a smooth, prolonged cruise, accelerating gently, coasting, turning and returning, the conclusion would be the same. The precise amounts would differ, of course, but the logic would not. Proper time depends on the path, not the excuse for the path. Whether you pirouette around a star or pivot with thrusters in empty space, the bend in your world line is what matters. The ship's accelerometers would register that bend. Anna could, in principle, integrate that sensation and predict exactly how much younger she'll be on return. She wouldn't need to peek at Leo's watch. The geometry is carried in her own experience. And so step by step, without a single equation, the Lorentz transformations fall into place as the only consistent rules for a world with a fixed light speed and equal laws for all gliding observers. Light clocks reveal the stretching of ticks. Symmetry tells us why each moving observer sees the other's time dilate. World lines break the tie at reunion. Airplanes and satellites sign the paperwork. Your phone's map is the practical epilogue. When Anna steps back onto the landing pad and Leo runs to meet her, their embraces are real, their years are real, and so is the difference between them. Not magic, not mistake, just the geometry of a universe that won't let anything outrun its brightest messenger and so reshapes time itself to keep the promise. If motion is relative, then why can't both twins insist the other was the one who moved? That simple question has bothered countless readers since Einstein's equations were first published. And it's what makes the twin paradox feel, at first, like a trick. Because if all uniform motion is equivalent, shouldn't Anna and Leo each see the other aging slowly? Shouldn't the paradox end in a draw? But it doesn't. When Anna returns from her voyage among the stars, she is younger. The difference isn't in how they perceive time, it's in the paths they took through space-time itself. Up to this point we've talked mostly about constant motion, smooth, steady gliding at a fixed speed. Special relativity handles that beautifully. You can move at 10,000 kilometers per hour, or sit still, and as long as your motion is uniform, physics looks the same in your cabin as it does in Leo's living room. That's the principle of relativity. But Anna's journey isn't uniform. She departs, coasts, turns around, and returns. The turnaround, that change of direction, is the key. That brief moment of acceleration breaks the symmetry. Acceleration is the act of feeling motion change. It's what pushes you back into your seat when a plane takes off, or what you feel in your stomach when a car brakes suddenly. In those moments, you can tell, directly, physically, that something is happening. You no longer float in a perfect frame of reference where everything feels still. You feel a force. That feeling is nature's way of telling you that your frame is no longer inertial. And in the twin paradox, that's the moment the universe quietly takes note. While Anna coasts away from Earth, relativity says she can consider herself at rest and imagine Leo and Earth moving backward. So far, so symmetrical. But when she fires her engines to slow down and reverse, the illusion breaks. She feels thrust, pressure, acceleration. Leo, sitting on Earth, does not. The two experiences are no longer equivalent. It's that brief burn, not the long cruise, that defines the asymmetry in their lives. Imagine it like this. The universe keeps a ledger, but instead of recording distance and duration separately, it records something called proper time, the total length of each traveller's path through space-time. Every world line, whether it's a straight cruise or a looping detour, has its own proper time between two meetings. The twin with less proper time is the one who experiences less aging. Acceleration changes the shape of that path. To visualize it, think of a simple diagram. Time running upward, space running sideways. Leo, who stays home, moves straight up the page. Time passes, but his position in space barely changes. Anna, on the other hand, shoots out diagonally, moving through space as well as time. Then she arcs back and meets Leo again. The total path she travels through space-time is shorter in its temporal length. The total proper time elapsed for her. That's not metaphorical. It's geometry. In space-time, the straight line between two events gives the maximum proper time, not the minimum. Just as the shortest distance between 2 points in space is a straight line. The longest time between two events in spacetime is also the straightest possible world line, the one with no acceleration. Leo's path is straight, Anna's is bent, and the bending makes her younger. It's an idea that's hard to visualize because our intuition comes from ordinary space, not spacetime. In three-dimensional space, detours make your path longer. In four-dimensional spacetime, detours, accelerations, changes of velocity make your experience time shorter. That's the core of relativity's geometry. To see why acceleration matters, imagine two travelers on a train platform. One train passes another smoothly. Each sees the other in motion. As long as neither train changes speed, there's no way to say which one is really moving. The situation is perfectly symmetrical, but if one train begins to brake, the passengers inside feel a jolt. The symmetry vanishes. That jolt reveals an absolute change in motion, a deviation from the straight inertial path. Acceleration, in other words, is motion that tells on itself. It gives you an unambiguous clue about your state in spacetime. That's why Anna, not Leo, is the one who must accept the shorter proper time. Her world line through the universe includes that turn, that deviation from inertial rest. Interestingly, Einstein realized that acceleration has a twin of its own, gravity. When you stand on Earth, you feel weight because the ground is pushing upward on you, keeping you from free fall. To a physicist, that's an acceleration, about 9.8 meters per second squared, 32 feet per second squared. In orbit, astronauts float not because gravity disappears, but because they're in continuous free fall, always falling around Earth. They feel weightless because there's no acceleration pressing against them. From this, Einstein made one of his deepest leaps, the equivalence principle. He proposed that acceleration and gravity are two sides of the same coin. If you can't tell the difference between standing in a rocket accelerating at 9.8 meters per second squared and standing on Earth, then gravity itself might not be a force at all, but simply the experience of being prevented from following a natural, free-falling path through spacetime. This realization opened the door to general relativity, where spacetime isn't just a stage. It bends and curves in response to matter and energy. But even within special relativity, where gravity is ignored, acceleration still marks the border between just moving and changing how time flows. When Anna accelerates to turn around, she effectively steps into a different set of reference frames, one where the coordinates of space and time shift. In one frame, she's rushing away from Earth. In another, she's heading back toward it. During that brief changeover, her concept of simultaneity, what she considers now, on Earth, leaps forward. From her point of view, Leo's clock suddenly advances by years in an instant. That's the mathematical reason she finds him older when they reunite. Even though the acceleration phase might last only minutes, it realigns her connection to time on Earth, adding up to decades of difference by the time she returns. Her clock didn't slow because she saw Leo's slow. It slowed because her path through space-time genuinely contained fewer ticks. We can think of acceleration as a kind of negotiation with space-time. When you accelerate, you tell the universe, "I'm changing my direction through time." And space-time responds by adjusting your proper time accordingly. It's not punishing you, it's keeping the geometry consistent. Proper time itself is worth dwelling on for a moment. It's a deceptively simple idea. The time measured by a single clock that moves along with you, unaffected by outside motion or observation. It's the time your heartbeat counts, your personal rhythm. No matter what others see, your proper time is what your body experiences. It's what Einstein meant when he said, "Time is what a clock measures." Each clock measures its own journey through the universe. There is no universal master clock keeping score. The beauty of proper time is that it's absolute for each traveller. Once you specify the path, the result is fixed. It doesn't depend on opinion, or perspective, or illusion. Everyone can agree on what each twin's proper time is, once the paths are known. What's relative is how different observers describe the events along those paths while they're apart. To get an intuitive grip on this, you can imagine space-time intervals as the distance between 2 points, not in space, but in a combined sense of space and time. In ordinary geometry, we find distance by combining differences in space. For example, a triangle's hypotenuse is shorter than the sum of its sides. In space-time geometry, time contributes with an opposite sign, which means that the longest proper time corresponds to the straightest world line. That's why a person who remains at rest, following the natural, unaccelerated flow of time, ages the most between two meetings. Every detour through space comes at the cost of less time experienced. It's as if the universe runs on a kind of exchange rate between motion and duration. Move more through space, and you buy it with time. Stay still, and you let time flow freely. That's the meaning of space-time intervals. They're the invariant distances between events that all observers agree on, even if they disagree on the separations in space or time alone. So while Anna and Leo argue about who was moving, they can both agree on one thing: the total space-time interval between their meetings. The universe keeps that number the same for everyone, and that number decides who aged how much. You could think of space-time as a strange kind of terrain. Leo strolls gently uphill along the slow slope of time. Anna sprints down and back across valleys of motion, climbing again to meet him. Her path covers more space but less time, and when they meet, they find the geometry exact. No trick, no favoritism, just the fabric of reality shaping itself to the rule that light's speed, and thus space-time's structure, stays constant. And here's something quietly profound. Acceleration doesn't need to be violent or long to matter. Even a brief pulse of thrust, a small bend in the path, can accumulate years of difference if it happens at relativistic speeds. What feels like seconds to one twin can mean decades to the other, not because of illusion, but because of geometry. This is what makes relativity so unsettling and so elegant. It doesn't contradict common sense. It expands it. It tells us that our everyday intuition about time, flat, uniform, shared, is a local truth, not a universal one. It works beautifully at walking speed, but the moment we step into the deep currents of space-time, the geometry shows its true shape. The twin paradox, when viewed through this lens, stops being a riddle and becomes a story of paths. Two lines start together, diverge, and reunite. One has felt acceleration, the other hasn't. One line is bent, the other straight. And in the curvature of those lines lies the answer. No paradox, just the poetry of motion through time. When Einstein first presented his theory of special relativity in 1905, it was written in the clean, straightforward language of physics: algebra, velocity, light. But only 3 years later, another mind would take those ideas and give them form. A vision so striking that even Einstein at first resisted it. That mind belonged to Hermann Minkowski, a mathematician who had once taught Einstein at the Zurich Polytechnic. In 1908, during a lecture in Cologne, Minkowski stood before a hall of physicists and said words that would echo through the next century. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows. Only a kind of union of the two will preserve an independent reality. With that, the universe gained a new dimension. Not physically, but conceptually. Space and time, once treated as separate entities, became fused into a single geometric fabric, space-time. It's hard to overstate how radical this was. Until then, time had always been thought of as a universal rhythm, the same everywhere, ticking invisibly beneath the movements of space. Space was the stage, time was the metronome. Even Einstein, in his early papers, spoke mostly of how clocks and rulers behaved when moving, not of a deeper geometric unity. But Minkowski saw something in Einstein's equations that others missed. Their mathematics already described a four-dimensional world. He simply named it. In Minkowski's hands, relativity stopped being a set of counterintuitive rules and became a landscape, something you could draw, explore, and measure. And with that, the so-called twin paradox ceased to be a paradox at all. To understand why, let's take a small step into that landscape. Imagine a sheet of graph paper. Let the horizontal axis represent space, your position, and the vertical axis represent time. Every mark on that paper is an event. a unique combination of where and when something happens. You can plot your life as a continuous curve, rising upward through time as you move through the world. That curve is your world line. If you stay perfectly still, say, sitting in a chair listening to this episode, your world line is almost vertical, straight up through time. If you start walking east, your line tilts slightly to the side. The faster you move, the more it tilts, until at the ultimate limit, the line representing a beam of light would lie perfectly diagonal at 45 degrees. Nothing with mass can ever tilt that far, because that would mean moving at the speed of light itself. Light defines the edge of what's possible, the boundary between can reach and forever beyond. Minkowski's insight was that motion through space and motion through time are connected by geometry. Every object, every person, every atom moves through space-time at a single constant speed, the speed of light, but divides that motion differently. When you're still, you move entirely through time. When you start traveling through space, part of that motion tilts away from the time direction. The faster you go through space, the less you move through time. That's time dilation, drawn instead of described. Now, picture our twins again. Leo stays on Earth. His world line rises nearly vertical, mostly through time, very little through space. Anna's world line shoots outward at a sharp angle, a long journey through space, a smaller climb through time, before bending back to meet Leo again. In ordinary three-dimensional space, Anna's journey looks longer. In space-time, it's shorter, and that's the key. In this geometry, proper time, the time experienced by each twin, is the length of their world line between departure and reunion. The longer, straighter path through space-time corresponds to more experienced time. The more tilted, looping path corresponds to less. No contradictions, no paradox. It's as simple and as beautiful as geometry. Minkowski's diagrams made this visible. In his space-time, time and space are axes just like the x and y of a map, but combined by a peculiar metric, one that treats time differently from space. Instead of adding distances together, as in ordinary geometry, space-time subtracts one from the other, reflecting how moving through space steals a little from your motion through time. This minus sign, tucked quietly into the equations, is the heartbeat of relativity. When physicists draw these diagrams, they often shade regions called light cones, the future cone above an event, the past cone below. Light defines these cones' boundaries, spreading outward at 45 degrees. Inside the cone are all the events you can reach or be reached by, limited by the speed of light. Outside the cone lie events that are forever inaccessible. No signal, no influence, no touch can cross that gap. Causality, the rule that cause precedes effect, is simply the statement that the universe lives inside its light cones. So where do the twins live in this picture? Leo's world line climbs gently upward through his own light cone, the simple vertical ascent of a person rooted on Earth. Anna's world line begins at the same point, then shoots outward along a steep diagonal, slicing across space-time at relativistic speed. At some distant point, she fires her engines, curving her path back, an elegant arc bending inward, until she re-enters Leo's light cone and their lines meet again. The shorter curve in space-time corresponds to Anna's shorter, proper time. It's not that her clock ran slow because of illusion. Her path through reality was literally shorter in the temporal dimension. Minkowski's diagrams show this as plainly as a ruler shows distance. This is why physicists no longer argue about the twin paradox. In four-dimensional space-time, the paradox evaporates. It's no more mysterious than two hikers taking different routes to the same summit, one taking the direct trail, one looping around the valley. The geometry decides who arrives later. Leo followed the straighter path. Anna's curved path gave her less time distance. The equations of relativity merely translate that geometric truth into numbers. The power of Minkowski's vision lies in how it lets you see time not as a river, but as a landscape, a terrain you can traverse, tilted and curved by motion and gravity. Each of us is always moving through it, tracing our own unique world line from birth to death. To you, the present moment feels like a single point, now. But in space-time, now is a slice, a surface tilted differently for every observer, depending on how they move. That's why simultaneity is relative. Two observers in different states of motion cut the space-time loaf at different angles. Their nows are not parallel. Einstein once described space-time as a kind of fabric, and while the analogy has limits, it's a good way to imagine it. When nothing disturbs the fabric, when no gravity warps it, world lines are straight. When something massive, like a planet or a star, bends the fabric, world lines curve toward it. What we call gravity is just the tendency of objects to follow those curved paths, seeking the straightest possible route, the one that maximizes proper time. That's why astronauts in orbit, though falling, feel weightless. They're simply following a natural, straight path through curved space-time, while we, standing on Earth, are forced to deviate from ours. Minkowski's geometry did more than tidy up Einstein's equations. It gave physicists a visual language to talk about reality. It's how we understand black holes, gravitational waves, and cosmology itself. Every modern description of the universe, from GPS corrections to the bending of starlight, rests on that four-dimensional scaffold. But there's something more human in it too. When you look at the twin paradox drawn in space-time, you realize it's not about motion at all. It's about perspective. Each twin's now slices through the other's life differently. When Anna turns around, her slice of now on Earth leaps forward, years passing for Leo in what feels like an instant to her. In Minkowski's diagram, that's just the tilt of her coordinate grid shifting. What seems like magic in time is simply geometry catching up. And in that geometry lies a strange comfort. Everything that ever happens, every moment, every heartbeat, every reunion, exists somewhere in space-time. Nothing becomes. It simply is, laid out in a grand four-dimensional whole. Past, present, and future are just the coordinates of where we stand in that structure. When Einstein's lifelong friend Michel Besso died in 1955, Einstein wrote to his family, "He has departed from this strange world a little ahead of me." That means nothing. People like us, who believe in physics, know that the distinction between past, present, and future is only a stubbornly persistent illusion. It's not cold comfort, it's geometry. The twin paradox, then, is a story of two world lines drawn through space-time, two lives moving differently through the same cosmic fabric. The reunion isn't a contradiction, it's the inevitable intersection of two distinct paths. One may be shorter, one longer, but both are true. Both belong to the same four-dimensional whole. And that's what Minkowski gave us, a way to see that the paradox was never really about twins, or clocks, or rockets. It was about the shape of reality itself. So when you imagine Anna's ship arcing through the stars, you can now picture it not as a voyage through distance, but as a curve traced across the silent grid of space-time, a luminous thread bending outward and back, returning home to cross another thread that has climbed more directly through time. In that crossing, one thread is slightly shorter, less time-travelled, yet both remain part of the same tapestry. The universe doesn't choose between them. It simply holds them side by side in the geometry of everything. It's one thing to imagine a story about twins and time, to trace elegant lines on a space-time diagram, and to marvel at the logic of it all. But eventually, physics must leave the chalkboard and touch the world. Relativity began as a thought experiment, but it earned its place in reality through experiments so delicate, so precise, that they seem almost poetic. Clocks flown around the world, particles that die slower when they move, satellites that must constantly correct for the flow of time just to tell us where we are. Einstein himself never doubted that time dilation was real, but for decades after 1905, direct proof was elusive. The effect is subtle at ordinary speeds, far too small to measure with early 20th century clocks. Yet the cosmos, as it often does, had already built its own laboratory. High above our atmosphere, cosmic rays, high-energy particles born in violent astrophysical events, constantly bombard Earth. When they strike atoms in the upper atmosphere, they create showers of secondary particles. Among them are unstable cousins of the electron known as muons. At rest, a muon lives for about 2.2 microseconds before decaying into lighter particles. That's barely enough time for light to travel 660 meters, about 2,165 feet. Not even a full kilometer, 0.6 mile. So, if muons were created 10 kilometers, about 6 miles above the ground, almost none should survive the trip to the surface. They should vanish long before reaching our detectors. But when scientists first measured the number of muons arriving at sea level in the 1940s, they found something astonishing. Far too many. It was as if the muons' internal clocks were running slow, and indeed they were, moving at more than 99% of the speed of light. The muons were experiencing time dilation. From our perspective on Earth, their lives were stretched, their decay delayed. From the muons' perspective, the story is equally consistent. They see the distance to the ground shortened by length contraction so they can reach it before decaying. Two views, one truth, perfectly symmetrical, both correct. Nature's own twin paradox, repeated billions of times a day above our heads. This cosmic ray experiment remains one of the most elegant proofs of special relativity. But physicists, being who they are, wanted to test it under controlled conditions, with machines, not the sky. So they built particle accelerators, rings and linear tracks where subatomic particles could be pushed to near-light speeds. In those accelerators, muons and other unstable particles were made to race around magnetic tracks at 99.999% of light speed, living far longer than they would at rest. The predictions matched perfectly. At CERN and other facilities, physicists measured time dilation so precisely that the agreement between theory and experiment reached parts per billion. In a universe governed by chaos and uncertainty, that kind of precision feels almost spiritual, the cosmos whispering back, "Yes, this is how I work." Still, to humans, equations about particles are one thing, clocks are another. The twin paradox isn't just about decay rates or cosmic radiation, it's about time itself. And so, in 1971, two physicists, Joseph Huffley and Richard Keating, decided to take Einstein's idea on a trip around the world. They borrowed 4 cesium beam atomic clocks from the US Naval Observatory, the most accurate timekeepers then available, and carefully synchronized them with a master clock on the ground. Then they boarded commercial airplanes. 2 flights circled the globe, one eastward, one westward. The eastward trip meant moving with Earth's rotation, increasing speed relative to the planet's center. The westward flight moved against it, effectively reducing that speed. Each direction, according to relativity, would affect time differently. After dozens of hours in the air and tens of thousands of kilometers, more than 25,000 miles, the clocks returned to Washington, D.C. The scientists compared their readings, and there it was. A difference of hundreds of nanoseconds, precisely where relativity said it should be. The eastward flying clocks had lost time, they'd aged less, because their velocity through space was greater. The westward clocks, moving slower relative to Earth's rotation, had gained time. The combined effects of special relativity, due to speed, and general relativity, due to altitude and gravitational strength, were both present, just as Einstein had predicted decades earlier. Huffle and Keating's results were later confirmed with even greater precision using more advanced atomic clocks, first on aircraft, then on rockets, and finally on satellites. Today, their experiment is no longer extraordinary, it's routine. Time dilation is now an engineering reality. Every second, the Global Positioning System, that invisible network of satellites orbiting 20,200 kilometers, about 12,550 miles above us, quietly proves the twin paradox again and again. Each satellite carries several atomic clocks, ticking with astonishing regularity, broadcasting timing signals down to Earth. Your phone or a plane or a ship receives those signals and calculates its position from the difference in arrival times. But here's the catch. If those satellite clocks ticked at the same rate as clocks on Earth, GPS would fail spectacularly. Because they're moving fast, their clocks experience special relativistic time dilation. They tick slower. Because they're higher up, farther from Earth's gravity, their clocks also experience gravitational time dilation. They tick faster. When you combine the two effects, the net result is that satellite clocks run about 38 microseconds faster per day than those on Earth. That doesn't sound like much, but light travels almost 300 meters, about 984 feet, in a microsecond. Without correction, GPS positions would drift by 10 kilometers, about 6 miles per day, more than 6 miles. Within a week, the system would be useless. So engineers pre-adjust the onboard clocks before launch to account for both relativity effects. The satellites tick slower on purpose so that once they're in orbit, moving fast and feeling less gravity, they align perfectly with Earth's time. Every navigation, every location pin, every map direction on your phone is a quiet testament to Einstein's theory. Relativity isn't a thought experiment anymore. It's the infrastructure of civilization. Sometimes the numbers are so small, nanoseconds, microseconds, that they seem almost trivial, but precision science is built on the accumulation of tiny truths. Each microsecond corrected, each atomic clock adjusted, each muon observed is a confirmation of the same geometry Minkowski drew over a century ago. A geometry where time is flexible, where motion sculpts duration, and where the twin paradox is not an anomaly, but the natural shape of the universe. As instruments improved, physicists kept tightening the screws of verification. In 2007, the National Institute of Standards and Technology, NIST in Colorado, built optical clocks so sensitive that they could detect time dilation from a height difference of just 33 centimeters, about 13 inches. Roughly the distance between a desk and a tabletop shelf. Lift one clock onto a shelf, and it literally ticks faster. Gravity, speed, height, all are stitched into time's rhythm, and in 2010, another NIST experiment confirmed the same effect with a difference of only 43 centimeters, about 17 inches, between two aluminum-ion clocks. For the upper clock, time flowed slightly faster, a fraction of a trillionth of a second per second, but measurable. The twin paradox repeated in miniature right there in a laboratory. It's astonishing when you think about it. What once seemed like a riddle for philosophers now shows up in the spacing of satellites, in the decay of particles, in the seconds of a lab clock moved half a meter, about 1.5 feet, upward. Einstein's thought experiments have become the routine corrections of engineers, and yet there's something poetic about the precision. Every tick of every clock, from the cesium fountains in Boulder to the orbiting satellites over the Pacific, follows the same principle. Proper time is personal. Each clock, each traveller, each twin follows its own rhythm through space-time. The margin of error in modern relativity tests is almost absurdly small. Muon lifetime measurements at accelerators agree with theory to better than 1 part in a trillion. Atomic clocks in orbit match predictions to a few nanoseconds per day. We have probed, measured, and verified the slowing of time to scales unimaginable a century ago and found no contradiction. If the universe were trying to hide a flaw in relativity, it's doing an exceptionally good job. There's a quiet dignity in that precision. Science doesn't just tell us stories, it holds them accountable. Every experiment is a conversation between imagination and reality. Michelson and Morley imagined an ether, and reality said no. Einstein imagined a flexible space-time, and reality nodded yes. Haffel and Keating imagined flying clocks, and the sky replied with nanoseconds of proof. Our satellites, our muons, our clocks all whisper the same refrain. The universe keeps time, but not equally. It's easy to forget how recent this understanding really is. When Einstein first published his theory in 1905, there was not a single clock on Earth capable of measuring time differences small enough to test it. A century later, we can watch time stretch and bend in real time, as delicately as watching a spider's silk tremble in the wind. Each experiment, from cosmic rays to airplanes to orbiting satellites, is a reflection of the same principle the twin paradox reveals. That time is not an independent flow, but a measure of the path each thing takes through space-time. Every confirmation adds another brushstroke to the portrait of reality that Minkowski and Einstein began to sketch. A world where motion and duration are inseparable, where every tick of a clock is an echo of geometry. And perhaps that's the most beautiful thing about all these proofs. They don't just confirm equations, they connect imagination to experience. They remind us that the universe, for all its vastness, responds faithfully to the smallest human questions, even the ones asked with a pair of wristwatches and a boarding pass. Relativity's truth doesn't live only in particle accelerators or satellites. It lives in the way we measure, in the way we synchronize, in the way we look up at the sky and realize that somewhere out there time itself is flowing just a little differently, and all we had to do to see it was to listen carefully to the ticking. The story of time dilation doesn't end with motion, because Einstein, brilliant and restless, realized something even more profound, that acceleration and gravity, those two seemingly different sensations, were not different at all. They were two faces of the same truth. This was the insight that led him beyond special relativity into what he called his happiest thought. It happened in 1907, 2 years after his miracle year. He was sitting in his office in Bern when the idea came to him. An idea so simple that, in his words, anyone could understand it, yet so deep that it reshaped physics forever. He imagined a man falling from a roof. As the man fell, everything around him, a ball, a tool, a key, fell at the same rate. For a few fleeting seconds, he would feel weightless. Inside his tiny frame of reference, there would be no gravity. He would float freely, just as astronauts do in orbit. Einstein realized that locally, in that small region of space and time, gravity could be transformed away. And then came the revelation. If gravity could be cancelled by free fall, maybe gravity was not a force at all. Maybe it was simply the effect of being prevented from falling freely. That was the seed of general relativity, the theory that space and time are not fixed arenas, but dynamic, flexible, and curved by mass and energy. To Einstein, matter told space-time how to curve, and space-time told matter how to move. And once again, the geometry of the universe took the stage. In this new picture, gravity wasn't a mysterious pull reaching across the void. It was the natural motion of things following the straightest possible paths through curved space-time. When you toss a ball upward, it slows and falls back, not because an invisible hand tugs it downward, but because its straight path, its geodesic, is curved by Earth's mass. When you stand on the ground, you're actually resisting your natural path through space-time. The floor pushes up on you, holding you slightly off your true trajectory. That push, that resistance, is what you feel as weight. It's an unsettling idea at first. You are being accelerated upward at 9.8 meters per second squared, about 32 feet per second squared, just by standing still. You are the one being forced out of your free fall trajectory. The apple that falls, meanwhile, isn't pulled. It's simply obeying geometry. And because time and space are part of the same fabric, wherever space bends, time does too. This means gravity isn't just the warping of orbits. It's the warping of time itself. A clock placed deep within a gravitational field, say, on Earth's surface, will tick more slowly than one farther away. This effect is called gravitational time dilation, and it's one of the most hauntingly beautiful consequences of general relativity. You can think of it like this. Imagine a series of clocks placed at different heights above Earth's surface. The one on the ground is deep in the gravitational well, closer to the center of Earth's mass, where space-time curves most strongly. The one on a mountain, perhaps 3,000 meters, about 9,800 feet, higher, is slightly less affected. To the higher observer, the lower clock appears to run slow. To the lower observer, the upper clock appears to run fast. Neither is wrong. Both are seeing time flow differently because their local regions of space-time are curved differently. This effect is small for Earth, but not negligible. For example, every second, a clock at sea level runs about 9 nanoseconds slower than one on top of Mount Everest, roughly 8,848 meters, 29,032 feet above sea level. That may not sound like much, but it's measurable. And as we've already seen, it's crucial for technologies like GPS. In the context of the twin paradox, gravitational time dilation adds another poetic twist. Imagine that instead of travelling through space, Anna stays in orbit near a massive planet, while Leo remains safely on its surface. Now both are experiencing time dilation, but for different reasons. Leo, deep in the planet's gravity, experiences slower time because space-time is more curved where he stands. Anna, in orbit, is moving fast, so her clock also runs slow, but due to her velocity relative to the planet. Depending on their exact altitudes and speeds, either twin could end up aging less. On Earth, for instance, astronauts aboard the International Space Station, orbiting at about 400 kilometers, roughly 250 miles altitude, experience both effects at once. Their speed through space causes their clocks to run slower than ours, but their weaker gravity causes them to run faster. The two effects nearly cancel out, but not perfectly. After 6 months in orbit, astronauts are about 0.005 seconds younger than people on the ground. It's a small difference, but it's real. And it's measurable. In deeper gravitational fields, though, the story changes dramatically. Near a black hole, for example, the warping of space-time becomes extreme. A clock placed just outside the event horizon could tick so slowly compared to one far away that seconds for one observer could mean years for another. This isn't science fiction, it's the same physics, simply magnified. Time itself stretches under gravity's hand. If Leo were to wait near a massive black hole while Anna orbited far above, the situation would resemble a cosmic version of the twin paradox. Only this time, it's not speed that separates their experiences, but curvature. Leo, deeper in the gravitational well, would age less. From Anna's perspective, his clock would appear to crawl, and from Leo's perspective, her clock would race ahead. When they reunite, if they could, the difference could be vast. The 2014 film Interstellar famously dramatized this effect. On a planet orbiting close to a supermassive black hole named Gargantua, an hour on the surface corresponded to 7 years for those waiting farther away. That's an exaggeration for cinematic effect, but not by much. For a black hole 10 million times the mass of the Sun, that ratio is physically plausible. Time really does flow differently in the deep gravity near such objects. It's the ultimate form of the twin paradox, written not in thought, but in the geometry of space-time itself. To understand why, we can return to the equivalence principle, the bridge between acceleration and gravity. Einstein reasoned that if you were sealed inside a windowless rocket accelerating upward through empty space at 9.8 meters per second squared, 32 feet per second squared, everything inside would mimic gravity. You'd drop a ball and see it fall to the floor, even though there's no planet beneath you. Light, shining from one side of the cabin to the other, would appear to curve downward, not because space was bent by mass, but because your accelerating frame bent relative to it. From the inside, acceleration and gravity would feel indistinguishable. That realization, that acceleration is locally equivalent to gravity, was the spark that allowed Einstein to extend special relativity into general relativity. He replaced the invisible force of gravity with the curvature of space-time. Objects in free fall aren't being pulled, they're simply following the straightest possible paths, geodesics, through a curved geometry. And acceleration, in turn, is what we feel when we resist that geometry. In a sense, every moment you stand upright, you're experiencing what Anna felt in her spaceship's turnaround. You're accelerating upward through space-time, feeling the resistance of the ground keeping you from falling freely. That's why your time, measured by a clock on your wrist, runs ever so slightly slower than it would if you were hovering a few meters higher. Even the act of standing still carries a trace of the twin paradox within it. Velocity-based and gravity-based time dilation are two expressions of the same geometry. One comes from moving quickly through space, the other from being in a region where space itself is curved. Both alter your world line through space-time, your personal path through reality, and both change how much proper time you experience. In special relativity, we learned that moving through space takes away from your motion through time. In general relativity, we learn that simply being near mass can do the same thing. The deeper you are in a gravitational field, the slower time passes relative to distant observers. The two effects are distinct but beautifully consistent, different angles of the same cosmic truth. Einstein captured this mathematically in 1915 when he finally completed the field equations of general relativity after nearly a decade of struggle. Those equations are complex, curved, and astonishingly accurate. They describe how matter tells space-time how to curve, and how curvature tells matter how to move. Out of them flow everything from the bending of starlight to the slow ticking of clocks on Earth, to the merging of black holes billions of light years away. It's worth pausing to remember. Einstein derived all this before we had even sent a plane across the Atlantic, before radar, before satellites. He imagined the curvature of space-time without seeing it, and then, as technology advanced, experiment after experiment confirmed it with astonishing precision. In 1960, two physicists, Robert Pound and Glenn Rebka, performed a beautiful test at Harvard. They measured the frequency shift of gamma rays traveling 22.5 meters, about 74 feet, downward in a tower. An infinitesimal change caused purely by gravitational time dilation. The shift matched Einstein's predictions exactly. Later, in 1976, a clock on a rocket launched to 10,000 kilometers, about 6,200 miles, altitude and back, confirmed the same effect to remarkable precision. Even in small doses, gravity stretches time. Today, satellites, planetary missions, and deep space probes all rely on those corrections. We don't just believe in gravitational time dilation, we budget for it. We code it into our software. We design our systems around it, and every time we do, we're living proof of Einstein's vision, that gravity isn't a force pulling on us from afar, but a curve in the very fabric of time and space beneath our feet. The twin paradox, once a puzzle of motion, becomes even richer under gravity's light. Because the real revelation is not that one twin moves and the other doesn't. It's that both live along different contours of space-time. Motion, mass, and curvature are all part of the same geometry, and time is simply what that geometry measures along each path. It's humbling to think that your heartbeat, your thoughts, the quiet ticking of your watch, all flow ever so slightly differently from those even a few meters above or below you. Time itself is local, sculpted by gravity, stretched by motion, and curved by the presence of everything around it. And as Einstein showed, acceleration and gravity are not separate forces in nature. They are simply the ways space-time reminds us that we are never truly standing still. If the twin paradox teaches us anything, it's that time is not the same everywhere, that motion, gravity, and curvature all shape how it flows. But it also teaches us something deeper, something more philosophical. The universe has rules, and among them is one sacred law, causality. Cause must precede effect. A signal cannot arrive before it is sent. And in Einstein's universe, that rule is not optional. It's built into the geometry of space-time itself. Causality is the thread that keeps the universe coherent. Without it, reality would unravel, cause and consequence could loop endlessly, events could undo themselves, and history could become a knot with no beginning or end. Relativity's strange treatment of time, with all its dilation and relativity of simultaneity, might seem to threaten that order, but in fact, it protects it. When Minkowski joined space and time into a single four-dimensional fabric, he also set a universal limit, the speed of light. That limit isn't arbitrary. It's the line that separates can influence from cannot. No signal, no matter, no information can travel faster than light without violating causality. Because if it could, then one observer's after could become another observer's before. And then paradoxes would not just be theoretical, they would be everywhere. Let's imagine it. Suppose Anna, still restless for adventure, wants to send a message to her brother Leo, not just across distance, but faster than light. If she could, relativity tells us that there would exist a frame of reference, a perspective, in which Leo would receive her message before she sent it. From his point of view, the effect would precede the cause. If he then replied instantly, his message could reach Anna before she decided to write in the first place. They could exchange messages that create themselves, a conversation with no origin. That's not just confusing, it's logically impossible. It's like a sentence with no author. And so, relativity closes that door firmly. The speed of light, about 300,000 kilometers per second, or roughly 186,000 miles per second, isn't just a speed, it's the speed of causality. It defines the edge of every light cone, the boundary of every event's influence. Inside the cone, cause and effect. Outside the cone, silence, forever unreachable. If you could somehow step outside that limit, you wouldn't just move faster. You'd move sideways through time. You'd be rewriting the order of events in the universe's own geometry. That's why Einstein's equations, while flexible and strange, never allow causality to be violated. Time can stretch, slow, or accelerate, but it cannot run backward in any observer's reality. No experiment, no particle, no rocket has ever found a loophole. Even nature's fastest travelers, the high-energy cosmic rays striking Earth's atmosphere at 99.9999999% of light speed, obey the law. They flirt with light, but never catch it. Still, the human imagination refuses to stop at the word impossible. Physicists, philosophers, and dreamers have all wondered, what if there were a way? What if the universe, somewhere deep in its geometry, left a door ajar? The first of these speculative messengers is the tachyon, a hypothetical particle that always moves faster than light. In the 1960s, as relativity matured and quantum field theory grew, scientists began to play with the equations, wondering what would happen if you extended them beyond the light speed barrier. The result was a mathematical ghost, a particle that could never slow down to light speed, just as ordinary matter can never speed up to it. A tachyon would experience strange physics. Its energy would decrease as its speed increased, and its mass would become imaginary. A concept that doesn't mean unreal, but rather mathematically complex. In theory, tachyons could send information backward in time. They could create what physicists call closed causal curves, where an event could influence its own past. That, of course, would lead to contradictions. If Anna could send a tachyon pulse to Leo's past, and Leo replied before she sent hers, the paradox would be complete. A loop with no origin. The universe would become a hall of mirrors, every cause echoing infinitely. For that reason, tachyons remain purely hypothetical. No experiment has ever found evidence for them, and most modern theories regard them as mathematical curiosities rather than real possibilities. In fact, the very structure of quantum field theory, which relies on causality for its foundations, tends to break down if tachyons exist. It's as if the universe itself forbids them, not through violence, but through self-consistency. But physicists didn't stop there. Einstein's general relativity allows for spacetime to bend and twist, and with that flexibility comes another kind of temptation: wormholes. A wormhole, in theory, is a shortcut through spacetime, a tunnel connecting two distant points. Imagine folding a sheet of paper so that two dots touch. If you could travel through the fold instead of along the paper, you could cross the universe in an instant. Wormholes appear as mathematical solutions to Einstein's equations, and they've become the darlings of science fiction, from Interstellar to Contact, for good reason. But wormholes come with their own warnings. They would require negative energy or exotic matter to stay open, something no one has yet found or created. And if a wormhole could connect 2 points in space, then by moving one of its ends, say, accelerating it near light speed, it could also connect 2 points in time. You could step through one mouth and emerge before you entered. A time machine, written in geometry. Physicists have studied this possibility seriously. Theoretical work by Kip Thorne, Michael Morris, and others in the 1980s explored what it would take to stabilize such a structure. They found that while the math allowed it, quantum effects, vacuum fluctuations, radiation, the energy density of space-time itself, might conspire to destroy any wormhole before it could become a paradox. As if the universe has a built-in defense mechanism. Whenever something threatens to violate causality, it collapses. Stephen Hawking even proposed a name for this cosmic safeguard: the chronology protection conjecture. the idea that the laws of physics conspire to prevent time travel on a macroscopic scale. In other words, the universe doesn't like paradoxes. It may flirt with them, but it never lets them grow up, and yet the temptation persists, because time travel, even forbidden, is irresistible to the human mind. It invites us to test logic itself. Consider the classic grandfather paradox. You travel back in time, meet your grandfather before he has children, and, through misfortune or design, prevent your own birth. But if you were never born, who made the trip? The paradox collapses on itself like a Mobius strip. Relativity alone doesn't allow you to perform such a feat, but it allows you to imagine the geometry where it might happen, in the curved, twisted spacetimes of wormholes or rotating black holes, where closed loops in time are mathematically possible, if physically improbable. Physicists call these loops closed time-like curves, and they've appeared in solutions such as Gödel's rotating universe and the Kerr metric for spinning black holes. In these scenarios, you could, in principle, follow a path through space-time that returns to the same event, your own past. But almost every expert agrees. The moment you try to make such a path real, quantum mechanics steps in and says no. Energy diverges, the geometry collapses, and causality survives. Still, the boundary between physics and fiction remains thin, a shimmering horizon where imagination and mathematics meet. We can't resist standing at that edge, looking across. Even Einstein himself was uneasy about the full implications of his equations. He once called the possibility of time loops disturbing, preferring to believe that nature would forbid them through some deeper law we have yet to discover. He was right to be cautious. Relativity redefines time, but it never abandons logic. It lets clocks run differently, but it doesn't let effects precede causes. There's a poetic balance to that restraint. The universe allows us to imagine miracles, tachyons, wormholes, paradoxes, but it quietly enforces a deeper harmony beneath them. In that harmony, causality is sacred. It is the rhythm of reality. Without it, the twin paradox itself would collapse. If Anna could send a message to her past self, "Don't launch, stay home," the story would dissolve into contradiction. But because relativity guards the light cone, the narrative holds. Anna's path, Leo's path, both move forward, always forward, through their own time. The universe may let them drift apart, stretch or reunite, but never reverse. And yet, even within that limit, relativity leaves us room to dream. Inside black holes, near cosmic strings, or at the Planck scale, the unimaginably small scale of 10 to the negative 35th meters, about 3 times 10 to the negative 34th feet, space and time may lose their classical meaning. Quantum gravity, the still unknown theory that unites relativity and quantum mechanics, could change everything. Perhaps, in that realm, causality itself might emerge as a property, not a rule, something that forms as the universe settles into order. If so, then our present understanding may be just a chapter in a larger, stranger story. But even if time travel remains forever impossible, the paradoxes it inspires are useful. They remind us that physics is not just about predicting outcomes, it's about exploring the limits of coherence. Every what if that collapses under contradiction teaches us something about how deeply consistent the universe must be. And there's something quietly comforting about that. Because a universe that forbids paradoxes is a universe you can trust. Its laws don't change mid-sentence. Its stories unfold forward, one event birthing the next, like the steady tick of a clock. So, when we imagine Anna looking back at Leo through the long light years of separation, sending signals that take decades to arrive, we can rest assured that the messages will always move one way, from past to future. They will stretch, delay, and bend, but never reverse. The universe doesn't cheat its own narrative, and perhaps that's what makes physics so profoundly human. We crave the impossible, to outpace light, to rewrite time, to change what has already been. And yet the same universe that limits us also gives us understanding, the one form of transcendence that doesn't break its own rules. The twin paradox, in the end, is a story about boundaries, the boundaries of motion, of time, of causality. And when we test those boundaries with equations, with thought, with imagination, we find not chaos, but order. The kind of order that allows life to happen, stories to unfold, and twins to grow old in their own unalterable rhythms of time. Because even if the stars bend space, even if time stretches and slows, the arrow of cause to effect, that sacred direction, always points forward. And perhaps that's all the time travel we were ever meant to have. By the time Einstein finished building his grand architecture of spacetime, physics had changed forever. But just as the ink was drying on that new geometry, another revolution began, one that would challenge not just our picture of the universe, but the very concept of what it means for something to happen. That revolution was quantum mechanics, and in it, time plays a very different role. In Einstein's relativity, time is dynamic. It bends, stretches, and flows differently for each observer. In quantum mechanics, time is rigid, an invisible stage on which probabilities unfold. One theory makes time part of the fabric. The other treats it as the thread holding everything together. Reconciling those two views has become one of the deepest puzzles in modern science. To the quantum world, time isn't a living dimension. It's a parameter, a number we plug into equations to see how things change. When you write down Schrödinger's equation, the fundamental rule that describes how quantum systems evolve, time is just there, silently ticking in the background. We don't ask what creates it or what it is, we just let it run like a metronome. The particles dance, time keeps the beat. It's a strange division because everything else in quantum physics is uncertain. Position, momentum, energy, all blurred, all probabilistic. But time? Time is certain. The one quantity that Einstein taught us was flexible becomes, in the quantum world, absolute. And yet, the two worlds must agree. Because quantum particles don't stop obeying relativity when they move fast. Their probabilities stretch, their decays slow down. Even their internal oscillations feel the flow of spacetime. One of the earliest hints that relativity and quantum mechanics could coexist came from studying decay rates of moving particles. Just as we saw with muons in cosmic rays, quantum systems also experience time dilation. A particle that might spontaneously decay in 1 microsecond at rest can last for many times longer if it's moving close to light speed. Its quantum clock slows down. This isn't just a macroscopic effect, it's built into the very equations that govern unstable quantum states. In 1940s accelerator experiments, physicists noticed that the lifetime of fast-moving pions and kaons, particles born in high-energy collisions, stretched exactly as Einstein predicted. The quantum decay constant, which measures how likely a particle is to disintegrate, changes with velocity. And the relationship matched the Lorentz factor to extraordinary precision. Even in the quantum world, time bows to relativity. But the quantum world adds its own kind of strangeness to time. In classical physics, a clock ticks whether or not you look at it. In quantum mechanics, measurement changes everything. The act of observing a system collapses its possibilities into a single outcome. And that raises a subtle question. If measurement defines when an event happens, does time itself depend on observation? Imagine a particle in superposition, not here or there, not yet decayed or already gone, but both at once. Until you measure it, you can't say when the decay happened. Its lifetime becomes a probability cloud spread across time, not just space. In this sense, even the moment of an event becomes fuzzy. At quantum scales, before and after blur. Causality still holds on average, but individual events defy our neat classical order. That uncertainty becomes even more fascinating when we look at entanglement, one of quantum physics' most mysterious features. Entangled particles share a state that connects them instantaneously, no matter how far apart they are. Change one, and the other reacts instantly, faster than light, at least in appearance. Einstein famously hated this. He called it spukhafte Fernwirkung, spooky action at a distance, because to him it seemed to threaten the very causality he had worked so hard to preserve. But decades of experiments have shown that entanglement is real, and that while correlations appear instantly, no usable information actually travels faster than light. The paradox dissolves in the details. You can't use entanglement to send a message into the past. It only reveals a deep connection between outcomes that were, in a sense, never separate to begin with. In 2013, researchers at the National University of Singapore tested this principle by sending pairs of entangled photons through different optical fibers, with one photon travelling at normal speed and the other slowed by a crystal lattice. The photons' shared quantum state endured. Even though one photon's path took longer in space, their joint behaviour remained consistent. Their now was not local, it was global. Later, in 2018, a team in China performed a similar experiment over 1,200 kilometers, about 745 miles, using satellites and ground stations. Again, the entanglement held. Quantum correlations transcended distance, yet never violated relativity. The message was clear. Nature allows deep connections, but not shortcuts. This raises a haunting thought. If time runs differently for moving observers, how do entangled particles, separated by that difference, still know how to correlate their outcomes perfectly? Some physicists argue that quantum systems don't evolve in time at all, that time itself emerges from correlations between systems. In this view, there is no master clock ticking in the background. Time is simply what we call the changing relationships between parts of the universe. It's a radical idea that time is not fundamental but emergent, that it arises from the quantum structure of reality, the way temperature arises from the motion of countless atoms. No single atom has temperature, but together they create it. Likewise, perhaps no single particle experiences time, but when you have enough of them interacting, time appears as a collective illusion. This concept, sometimes called the thermal time hypothesis, has found intriguing support in modern theoretical physics. Carlo Rovelli, one of its strongest advocates, describes time as an approximate concept that applies only at macroscopic scales. At the deepest level, near the Planck scale, space-time might not even exist in any familiar sense. Instead, the universe could be a web of quantum events, nodes of interaction, probabilistic relationships, from which the smooth flow of time emerges only when viewed from afar. In this picture, Einstein's space-time and Schrödinger's quantum clock are both approximations, different shadows cast by the same unseen reality. And the twin paradox, when seen through this lens, becomes something even more beautiful. It's no longer just about moving clocks or curved geometry. It's about how systems record change. Leo's and Anna's clocks don't disagree because one is wrong. They disagree because each represents a different way the universe keeps its memory. Proper time, that personal measure of duration, may itself be an emergent quantity. A kind of bookkeeping the universe uses to make sense of correlations between events. Quantum experiments keep testing this idea. In 2020, researchers in Vienna used entangled atoms to probe time dilation directly. They placed pairs of ions in separate traps and moved one of them at high speed. When compared later, the quantum coherence, the delicate phase relationship between their internal states, showed the precise time shift predicted by relativity. Time dilation measured not with clocks, but with quantum phase. Even in the subatomic realm, Einstein's geometry holds. But the quantum world adds a whisper. Maybe geometry itself is born from entanglement. At cosmological scales too, physicists suspect that time might emerge from quantum information. In loop quantum gravity, space-time is described as a network, a spin foam of discrete quantum interactions. Each node is timeless. What we perceive as flow is simply the changing pattern of connections. In the early universe, before matter condensed and clocks could tick, time may not have existed at all. Only relationships, only probabilities waiting to become history. And yet, when we zoom back to our world, to seconds, minutes, years, time feels undeniably real. We grow older, stars burn out, twins age differently. If time is an illusion, it's the most persuasive illusion ever made. Perhaps that's why physics struggles so deeply to define it. It's not just a variable in an equation. It's the medium of our existence. Einstein once wrote that for those who believe in physics, the separation between past, present, and future is only a stubborn illusion. Quantum mechanics pushes that idea even further. Maybe the separation between before and after is a matter of perspective too. Maybe everything, the birth of the universe, this moment, and every moment yet to come, exists together, stitched into a timeless whole by entanglement itself. If so, then time isn't a river, but a pattern. Not something that flows, but something that emerges when part of the universe observes another part. It's a dialogue between systems, not a property of any single one, and we as observers are part of that dialogue. Each measurement, each act of noticing, each flicker of awareness helps define what now means. In that sense, we are participants in the creation of time. So, what does this mean for our twins? Perhaps Anna's long journey and Leo's waiting years aren't two separate experiences at all, but two perspectives on the same quantum web. Two ways the universe keeps track of change. Their differing ages are not contradictions, but different readings of the same cosmic wave function. And if time itself emerges from entanglement, then maybe, in some deep quantum sense, the twins were never truly separated to begin with. The question remains, is time fundamental, or is it something the universe dreams up so that change can make sense? We don't yet know, but we do know this. Even if time is born from the relationships between things, it feels utterly real inside the dream. It carries us, shapes us, defines us, and the twin paradox, that strange, elegant story of two clocks disagreeing, is our clearest reminder that time is not what it seems. Maybe it's not a single thread we move along, but a tapestry we help weave, stitch by quantum stitch, observation by observation. And perhaps one day, when physics finally unites the quantum with the cosmic, we'll discover that time, that steady, flowing illusion, was never the stage at all, but the performance itself. The story of the twins isn't really about physics anymore. By now, we understand the geometry, the equations, the precision of the clocks. We know why one ages slower, why time bends, why motion sculpts duration. But beneath all of that, the twin paradox hides something more human, a quiet ache about separation, memory, and return. Because what could be more poignant than leaving and coming home to find that time itself has betrayed symmetry? It's one thing to imagine a clock ticking differently, or a muon surviving a few extra microseconds. It's another to imagine watching someone you love grow old while you remain almost the same. That's not just physics, that's tragedy, longing, and awe woven together. If Anna returns to Earth decades later to find Leo grey and lined, she has crossed not just a distance in space, but a distance in experience. The world she left has aged without her. The people she loved have lived entire lifetimes while she lived only years. For her, time was generous. For them, it was relentless. That imbalance, that emotional geometry, is what gives the twin paradox its depth. It's a story about the one thing we can't share equally, time itself. And in that way, it reflects a truth we already know intimately. We all live in slightly different times. Our days pass at different rhythms, for the young, for the old, for the restless, for the still. We measure them with the same clocks, but we feel them differently. Relativity just makes literal what the heart has always known. Einstein's theory may describe the physics of time, but our minds carry their own relativity, the way moments stretch or collapse depending on emotion. A joyful hour passes in a blink. A moment of loss can feel like an eternity. Psychologists call this subjective time, and though it has nothing to do with velocity or gravity, it mirrors the same idea. Time is not absolute. It bends under experience. Studies in cognitive science show that when our brains are flooded with novelty, attention, or emotion, they mark time more densely, more memories per moment. That's why childhood feels endless. Every day is filled with new impressions, unfiltered and vivid. As we age, familiarity compresses time. Days blur, memory thins, and the years accelerate. Our internal space-time contracts. The twin paradox, in that sense, is just another version of this. Two paths through life, one dense with change, one slow and continuous. Both valid, both true. Perhaps that's why the idea of time dilation resonates so deeply in art and literature. It's not just the science that captures us, it's the metaphor. We understand separation. We know what it's like to come back to a changed world. One of the earliest literary echoes of the twin paradox predates Einstein by centuries. In the 8th century Japanese tale Urashima Taro, a fisherman visits a palace beneath the sea, staying there for what feels like a few days. When he returns, centuries have passed on land. The story, meant as a myth, foreshadows the very essence of time dilation, a place where time runs differently, where the traveller's return is both a miracle and a loss. Centuries later, the theme would recur in European folklore, in the tale of Rip Van Winkle, who falls asleep in the Catskill Mountains and wakes 20 years later to find the world transformed. Even before relativity, humanity dreamed of leaving time behind and of the melancholy that comes with it. When Einstein's ideas finally gave scientific form to those dreams, artists and writers rushed to explore their implications. Science fiction became a playground for the emotional consequences of relativity. Robert A. Heinlein's Time for the Stars, 1956, tells of twins communicating across light years, one travelling on a relativistic ship while the other remains on Earth. As one grows older and the other barely ages, the novel captures both the wonder and the sorrow of time dilation. The impossibility of truly sharing life when time itself refuses to agree. Later, the theme found its way into cinema, perhaps most memorably in Christopher Nolan's Interstellar, 2014. In one of the film's most haunting scenes, astronauts visit a planet orbiting near a black hole where gravity slows time to a crawl. 1 hour there equals 7 years on Earth. When they return to their ship, their colleague, who has waited in orbit, has aged decades. He's older, weary, lonely. They're barely changed. It's the twin paradox rendered emotionally, the heartbreak of asynchronous aging. The film's science advisor, Kip Thorne, ensured the scenario was based on genuine physics. The numbers are exaggerated but plausible near a supermassive black hole, and the emotional truth is undeniable. Time dilation may be a feature of physics, but it is also a metaphor for the distances we all live with, the way we grow apart, even while moving through the same universe. In literature, the paradox often serves as a mirror for loneliness. The loneliness of those who move faster, think deeper, or dream further than those around them. It's the artist's paradox, the explorers, the scientists. To leave is to change your time. To return is to find your home changed in your absence. Even Einstein himself, though devoted to logic, understood the poetry of that. In 1922, he wrote that people like us who believe in physics know that the distinction between past, present and future is only a stubbornly persistent illusion. It's one of the most quoted lines in all of science, not because it's technical, but because it's comforting. It suggests that even as time separates us, the universe holds all moments equally, that nothing truly vanishes. Every hug, every laugh, every goodbye, preserved somewhere in Spacetime's eternal archive. Artists have long chased that idea, that memory might defy time. Salvador Dali painted clocks melting under the sun in The Persistence of Memory, 1931, as if mocking the idea of permanence. He once said he was inspired by the soft watches of the cheese, but critics saw something deeper, the surreal elasticity of time itself. Dali's painting feels like relativity turned emotional, space melting into dream, minutes dissolving into memory. Music too has its versions of time dilation. When we listen to a song that moves us, minutes vanish or expand depending on how deeply we fall into it. Time becomes subjective, stretched by emotion, a tiny echo of the same relativity that governs stars. Even everyday language reflects this intuition. We say time flies, drags, stands still. We don't talk that way about distance or mass. We know instinctively that time is something we experience, not just measure. In that sense, time is both a quantity and a feeling. Physicists measure it with cesium atoms and coordinate systems. Poets measure it with loss. Both are right, Every second that passes is both an objective duration and a subjective moment, the meeting of two realities, the external and the internal. And maybe that's the truest resolution of the twin paradox, that time can be both scientific and emotional, both universal and personal. Einstein's equations describe how time flows differently for two observers moving at different speeds. But anyone who has waited for someone to return, from war, from travel, from a long silence, already knows what time dilation feels like. Waiting stretches time, absence deepens it, and the reunion, when it comes, feels both too brief and impossibly long-awaited. In that sense, we've all lived our own twin paradox, one way or another. Psychologists studying isolation in long-term space simulations have noticed something similar. When astronauts or analog crews spend months in confined environments, their perception of time often warps. Days blend, circadian rhythms drift, and moments of contact, a message, a call, a signal from Earth, feel like islands in an endless sea of duration. Even at ordinary speeds, our minds are not immune to relativity. It's possible that if Anna and Leo were real, their reunion would be filled not just with wonder, but grief. Leo might have children grown old, friends long gone. Anna might carry memories that still feel fresh, only to realize that no one else shares their recency. The universe would have kept its promise, the physics would be perfect, but the cost would be loneliness measured in years. That emotional truth is perhaps what makes the twin paradox so timeless. It reminds us that time isn't just what the universe does, it's what we feel passing through us. Our memories are the clocks that count it. Our connections are the light signals that keep it synchronized. And every reunion, whether across light years or across a room, is a small miracle of space-time alignment. For all its abstraction, relativity is a profoundly human theory. It's about perspective, about realizing that your now is not someone else's now, that the world looks different from every frame of reference. Isn't that empathy, in a way, the ability to see that others move through their own time shaped by their own motion and gravity? The equations may speak of clocks and velocities, but behind them lies something emotional, the understanding that no two lives flow at exactly the same pace. And yet the universe, in all its complexity, still allows them to meet, to share a moment, to overlap their worlds, however briefly. Time, then, is not just a measurement, it's a meeting point, a rhythm that connects motion and meaning, an emotion written into physics. And maybe that's why the twin paradox continues to haunt us, not as a problem to solve, but as a metaphor for being alive. Because every goodbye carries a little time dilation, every memory is a message sent forward through the curvature of life, and every reunion is an act of relativity, two world lines crossing again, however briefly, in the grand geometry of existence. By now, the twin paradox has carried us from rockets to particles, from clocks on airplanes to the quiet bend of gravity itself. But relativity's reach doesn't stop with the human scale. It extends across the entire universe, shaping how we see galaxies, how we measure cosmic history, and how we wonder what now even means on the grandest scale. Einstein's relativity is not just a local theory of motion, it's the foundation of cosmology. Every observation we make of the cosmos, every image of a galaxy billions of light years away, is filtered through the geometry of space-time. And that geometry is not static, it's expanding. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, their light stretched towards the red end of the spectrum. This cosmic redshift was the first observational proof that space-time itself is stretching. It's not that galaxies are flying through a pre-existing void, it's that the fabric of space between them is growing. If you reverse that expansion, you arrive at a beginning, the Big Bang, about 13.8 billion years ago. But here's the twist. In a universe where space is expanding, simultaneity, the idea of now across the cosmos, becomes even more slippery. There is no universal present moment that sweeps through all of space. Each observer, wherever they are, defines their own cosmic time according to their motion and gravity. Two galaxies billions of light years apart may each believe it's today, but their definitions of today are tilted in space-time, misaligned like two overlapping shadows. That makes cosmology, in a sense, a giant version of the twin paradox. Every region of the universe experiences time differently, depending on how it moves within the overall expansion. A clock in a galaxy cluster, slowed slightly by gravity, ticks differently from a clock in the emptiness between galaxies. And even here on Earth, we exist in a region where cosmic time and local time overlap only approximately. We often imagine the universe as an expanding balloon, but a more accurate picture would be a curved, four-dimensional tapestry where every patch stretches at its own rhythm. In that cosmic dance, there is no single tempo, only harmony. Nowhere is that curvature more dramatic than near black holes, the ultimate expressions of Einstein's equations. At the edge of a black hole, gravity warps space-time so severely that time itself slows almost to a stop. An observer falling toward the event horizon would appear from far away to freeze in time, light from their final moments stretched and reddened into eternity. But from their own perspective, nothing special happens. They cross the horizon in finite time, unaware that the universe outside has aged into the far future. It's a real-life version of the twin paradox pushed to its extreme. One twin hovering near the event horizon could experience minutes while the other, orbiting safely afar, might watch centuries pass. The difference isn't theoretical, it's written into the geometry of space-time. And though we can't yet send humans there to measure it, we've seen the fingerprints of time dilation around real black holes. The light from gas swirling around the supermassive black hole in galaxy M87, captured by the Event Horizon Telescope, shows the same gravitational redshift predicted by relativity more than a century ago. Time slows near gravity's edge. The universe keeps its promise. But we don't have to look that far to test time's elasticity. In laboratories on Earth, physicists now build clocks so precise that they can detect time dilation from a difference in height of just 1 millimeter, about 0.04 inches. At that scale, the effect of gravity on time, once thought immeasurable, becomes something we can literally watch happen. In 2022, scientists at the National Institute of Standards and Technology, NIST, used optical lattice clocks, each built around a few hundred strontium atoms, to measure gravitational time dilation across a vertical distance of just 1 millimeter. The difference was less than a trillionth of a second, yet it matched Einstein's equations perfectly. Time is not only flexible at cosmic scales, it's flexible right here in the lab, between your feet and your head, and these experiments keep improving. Each generation of atomic clock becomes more stable, more exact, pushing humanity closer to what physicists call the Planck time, the smallest possible unit of duration, about 10 to the power of minus 43 seconds. At that scale, our understanding of physics collapses. The smooth fabric of space-time, so elegantly described by Einstein, would ripple and foam under quantum uncertainty. We don't yet know what time means there. This is where modern physics finds itself today, at the boundary between relativity and quantum mechanics, where both are right but not yet reconciled. One describes the large, one the small. One treats time as geometry, the other as a parameter. Between them lies an uncharted frontier, the quantum nature of time. The leading theories of quantum gravity, string theory, loop quantum gravity, and newer frameworks like causal set theory, all suggest that time, like space, may be discrete rather than continuous. That what we experience as the smooth flow of seconds might actually be the sum of countless quantum ticks, flickering like frames in a cosmic film reel. But no one yet knows how those frames link together to form the seamless movie we call reality. Einstein's relativity remains unbroken, confirmed by every experiment, every satellite, every black hole image. And yet, physicists sense that it is incomplete, that beneath the space-time it describes lies a deeper layer, a quantum foundation where time might not even exist as we know it. Perhaps, as some physicists suspect, the flow of time is an emergent phenomenon, rising from the collective behavior of quantum events, just as temperature arises from molecules in motion. If so, then the twin paradox is only the surface of a much deeper mystery. Why does time feel like it flows at all? In cosmology, relativity gives us the grand story, from the first microseconds of the Big Bang to the accelerating expansion driven by dark energy. But it doesn't tell us why the universe experiences time as an arrow, always moving forward, never back. That mystery, tied to entropy and the quantum measurement problem, remains unsolved. It's as if the universe knows how to keep time, but not why it prefers one direction. And so, at the edge of modern physics, we find a paradox that mirrors the twin story. We've measured time's flexibility, charted its curvature, watched it slow near black holes, and counted its nanoseconds with perfect accuracy. Yet the deeper we look, the more it slips away. No longer a river, but a pattern woven from something even more fundamental. Perhaps one day, when the quantum and the cosmic finally meet, we'll discover that time is not the backdrop of the universe, but one of its most beautiful illusions, a melody that emerges only when matter, energy, and consciousness align to listen. When Anna's ship finally returns to Earth, the light of her home star feels both familiar and strange. The oceans look the same, the continents still rest beneath their clouds, but the world has moved on. Decades have passed for Leo, only a handful of years for her. He waits by the landing field, his hair grey now, his face marked by the time that she has outrun. When he sees her step out of the ship unchanged, he laughs, a tired, astonished laugh that carries both joy and something like grief. For a moment, the two of them stand quietly, the air between them heavy with what time has done. She touches his hand, and it feels like reaching across the universe itself, not because of distance, but because of everything that has happened while she wasn't there to see it. The paradox, at last, isn't in the clocks or the math. It's in this moment. Two lives that once moved together, now out of rhythm. Einstein's equations can explain the difference in their ages perfectly. They can tell us why her heart beat fewer times, why her atoms oscillated more slowly. But they can't explain the silence that follows, the human side of time. Because behind every second that science can measure, there's another kind of time, the kind we feel. The twin paradox was never a contradiction. It was a mirror, showing us that time isn't absolute, that motion and gravity and perspective all weave it differently for each of us. But it also shows something deeper, that reality itself is relational, that the universe doesn't hold a single, shared now, only a tapestry of many. Each thread true in its own frame, each path through space-time unique. When Anna and Leo finally sit together again, one old, one young, they're not separated by injustice or mystery. They're simply two travellers who took different routes through the same universe. And their reunion, quiet and trembling, completes the experiment in a way no equation ever could. Because the twin paradox isn't about distance or speed or even time itself. It's about connection, how fragile it is, and how precious that two beings can ever share a single moment at all. So perhaps, after all the geometry, the math, and the light cones, that's what relativity leaves us with, a strange kind of tenderness. The understanding that time is not fixed, but it is real, because it's what allows us to meet, to part, and to remember. Thank you for listening to this episode. If you enjoyed drifting through this story, through science, history, and the quiet wonder of time, I'd love to know where you're listening from and what time it is there right now. Leave a comment below, and if you'd like more nights like this one, subscribe. It helps this journey continue. Wherever you are, I hope this leaves you with a sense of calm and curiosity, because even in a universe where time bends and breaks and refuses to stay the same, you still have this moment, right now, yours to keep. Rest well, and until next time, sleep peacefully somewhere in space-time.